Good. So where were we? Basically, these things didn't work well, and I think I kind of know another way that I could do these instead of what am I doing here? Okay, so CCZ that goes away. So a possible way to do these, I'm assuming, is that we basically, well, we kind of say this is an operation, right? So we're saying uh, obz obz is these, right? And then we're kind of now. I mean, that's probably ways to write this in less lines of code, but this is just the dumbest way that I can think of. And now I just basically kind of say for I guess you can say 4x in range 0 to qubits minus 2. Can we just do now obz controlled by qubits x? Can you do I probably can do something like this, right? So you're kind of putting the operation in here, and then you're just adding multiple controls. Qubits x. Does this work or not? And here would be kind of the same idea. I'm gonna keep those lines commented right now. So this is just this, yeah, exactly. So the qubits, exactly. And so now what I was testing, basically, I was testing b qubits 3 and b values 1 qubits. So creating the qubits, we're creating the circuit, we appending the Grover iteration. That's probably, let's see if this is gonna run. No, flatten to ops or moments. Not an operation or iterable. Line 43. Append, okay. What if I just, can I just print that? Well, so it's yielding all this stuff. That should work. Grover Oracle is yielding. Oh yeah, here we're not yielding anything, but maybe this is the reason. So I just probably have to do something like yield the operation, probably. Probably. But if not, oh yeah, come on, it worked. Look at these. So what do we have here? Hadamard, Z, Hadamard. Why? What is the Z doing here? What is the Z doing here? What is the Z doing here? Oracle. What is this doing here? So, what is this doing here? Oh, it's just the Z. It's not being controlled? No, it's missing the controls. It's actually missing the controls. There should be control Z. What have I done here? X range offset controlled by qubits X yield OPZ. So what if I just do this? Grover Oracle. So what am I getting here? That's not good. Whereas if I just do the Grover iteration and I comment these out, and I run the code, now I should get just the actual diffusion operator. And now it's also not working. Because this is what's getting in there. So you're still getting just these controlled by. Oh well. Should probably reassign the value. Now we should be good to go, I think. That works. Oh yeah. Oh yeah. Not entirely sure though. So maybe I should do -1. So what if I use the oracle, just the oracle? Let's just print the oracle. Let's just print the oracle, see what happens. Okay, now it works. Beautiful. So if I just say number of qubits 10, and we run the code. And what is about the number of values? Okay, that's still something that I gotta, okay, yeah, that's cool. Okay, so I found a way to make a multi-control X. It's pretty neat. Good. What else? Yeah, so basically, now the question is if I want to, because if I've achieved that already, so I can get rid of these. I can get rid of these comments in here. I can get rid of these. So once I know that, now the next step is how can I just give a number in NB values and then let the oracle come up with this? Because basically, you know, this is kind of like a sort of multi. It's like a multi-control Z. But now, what if I want to just say, for example, you know, to flag like 5 values, right? So I have to kind of start with, okay, so how many values do I start with? And so this should always be the first one. And then the next one should be kind of peak sort of 1 qubit and turn it into like a sort of surrounded with X gates, right? So you get that effect of let's say, you know, the anti-control, right? Yeah, so I should probably, I don't want to put it into a function because I don't really see the reusability of these, to be honest. So I would just assume, now I would just kind of say, you know, kind of like if NP values is bigger than 1, right? What we need to do is, or I'll say while NP values is bigger than 1, what we can do is, well, we need to kind of start from qubit 0, right? We can just randomly pick qubit 0 and then thinking ideally you would turn that into a binary string, and then you would kind of use that binary string to say what's the element you're flagging, for example, right? So there where you've got zeros. But an easier first implementation is if we only allow, for example, if we've got like, say 5 or 6 qubits, we only allow to kind of flag up to 6 elements. But that's just a just putting the problem for later on, because I wanted to kind of basically, do some kind of like accuracy tests on these new way of, or this slight modification of quantum counting. So I would just rather go this way, basically. So it's the most generic approach. So I need help. I need Google. So Python. So cast into a binary representation. Binary decimal to binary. Right. If you want a textual representation, a key number is binary. Use bind with bean. Okay. And so this basically is a format for painting the leading zeros. F string. So what is this? F string. New format is string literal. F string is string literal that is prefixed with F or F. The strings contain replacement fields with expressions. Name friend, name R. Name friend, name R. Numerical literals. Being integer. Being integer. Being integer. So what if you just, you mean what? Int B. Zero B format 47. So you would do something like these, or what? So you would do something like, so you would say format NB values, right? And that would be the binary representation. And so what you would then do is you would say, so for and now you want to iterate over those binary values, right? No. So you would say, so you'd say while NB values is bigger than 0, right? Do I have to do this? Yeah. Then basically get the binary representation of that. And at the end, we'll just update NB values, okay? -1. And so in between, we'll just now say for X in range from 0 till till b what size, or what's the string size? Python length, probably Python string length is len, right? Nice len string, okay. So now we're saying basically, so we have the index and we say if ex equals 0, then do that basically. Then mm, 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 mm. So then kind of so we need to track whether the z has been added, right? False. Is it false written like this in Python? Yeah, false. So if it's 1, then basically you'd say if if the z hasn't been added, right? What you now do is you actually do that, right? So then you apply these in the qubit in the position x, okay? And then you say z added equals true, and good. And so else, is it if else like that in Python? Python if else statements. So how long are we? But I just want to keep track of the time. Cool. If else. If elif, okay, or elif, or just else, okay, else. So else. Oh, here by the way, also else is just a control, right? So what you want to do is you want to basically have this obz in here, and then you kind of say else obz equals obz controlled by qubits x. Now, good. There's a lot of edge cases where you probably want to error control some of those things, but just I'm going to assume it's working. I'm going to assume it's always going to get in here first, right? So you should not really check whether obz is defined or not. Else, if it's 0, right? Well, we just basically do. What we just basically do is. Wait a second. So what are we doing here? X. So what we're gonna do is we're gonna we're gonna I don't know if this is gonna work, but we're basically gonna say circ.x qubits x. Okay, so we apply an x gate, then we update the obz, and then we apply another circ x on qubits x. So we're basically doing a sandwich with x, so we get like the anti-control. I have no idea whether this is actually going to work or not. So you're iterating over the range, blah, blah, blah. And so we kind of, okay, then we close it up by just decreasing that so we can get out of the loop. Okay, so the only thing that it's doing is for the first instance of 1, we're going to add like the actual Z gate in there. Otherwise, it's going to be a control gate. And if it's a 0, it's an inverse control. The problem is if it's all zeros, right? So this is kind of an edge case, right, where you want to basically it's bigger than 0. It's bigger or equal than 0. So this is a special case. I think that's not going to work out. So if NB values equal 0, we're going to just do something here. If not, else, and we're doing all this stuff in here. Well, that's not exactly. Then what we're doing is basically, so we're just doing these, to be honest. Kind of need to yield that, right? Don't we? No, we cannot yield that, to be honest. So what we need to do is, okay, so give me a second. So what we need an X layer, right? Which is basically an X layer, which is basically it's just a list. And so what we need to do is we need to how can we do this in a nicer way? Because I want to have like if NB values equals 0, I want to yield basically a layer of. I think I know. I think it's going to be easier. I think I know. Yeah, I think I know a way easier way to do that. So let me just give me a second. So I'm gonna yield. Yeah. I have it. So I'm gonna yield circ. So first we want to yield all the X gates. Then we want to yield. So circ X for qubit X. How can I compact that? I'm not really good with compact notations. So what I could also do is so just basically this, so just basically these, to be honest, guys, it's easier. I know that's programming 101 for a lot of you, but well, it probably seems like this. And it's been a long time actually without programming. So I'm going to do these. I'm going to say if, so if basically, we need that. This we need definitely. And so we're going to say if, so if bx, right, equals 0, then we're going to just basically yield circ x. I know it's a lot of yields, and I know it's probably inefficient, but it's fine. So this basically yields an x for each qubit where there's a 0 in here, right? And so that's kind of like first X layer. Then we're going to do a last X layer, which is going to be exactly the same. Last X layer, and in between, we're just going to have like a multi-control X. That's it. It's way too overcomplicated. So we're kind of gonna have we're just gonna have these, right? I think that that's the job, to be honest. We can try. So we can try, right? So that should do it really. So if NP values is 1, right, you should just have, okay, let's try. So let's just do Grover, Oracle. Let's just do Oracle, and let's just say we're going to have 5 qubits and first 1 value, right? So this 1 value should just go here, get that. Okay, but how do I know the leading zeros? How do I add the leading zeros? I want to have the leading zeros. Crap. But it shouldn't be a problem, to be honest. Because, okay, so x is not going to be x. What we want in here is we want to process that from the end. So QB, okay, so we're going to start from the last element of the binary string, right? Because everything else is going to be zeros, yeah, but then we don't have the x negative. No, if I have a 1, 0, 0, 0, 1, yeah, I need that. Okay, so wait a second. So I need that to be, I need that to be, I need that to be exactly, decimal to be to binary, binary. So what's is there like an accepted answer to this? Because I want to have the leading zeros, right? I want to have the leading zeros. I want to have the leading zeros. Do, 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 do. 6 years ago. Zfield call. Okay, so you can do mutability, flexibility, binary I. What is these though? Zfield 16. Okay, but here you know. Come on. Okay, so what is this? When you want an n-bit representation, get being lambda x. If you want a textual representation without a 0 bit race, you can use these. What is lambda x? What is these? Does this work at all? So what if I just don't do any here? Just let me test something quickly, okay? So I'm just gonna do these blah blah blah. I'm not gonna print these. So I'm just gonna say quickly. So Python lambda. What is this? Python lambda. Python lambda. Lambda is a small anonymous function. Okay, this is just a quick way to create a function. Okay, that's cool. Okay. Okay. Ah, cool. Interesting. So get bean or print get bean of like say 3 with like 5 qubits, right? So run this. I just want to quickly know if this works. That's awesome. That works. Cool. So Cool. Okay, so we'll get these in here. Basically, know that we could just okay, whatever. So we'll just put it in here, and then we'll just say get binary. Okay, so we're gonna get binary representation of NB values. That's it. Cool. Okay, so this goes away. And now we're going back here, and back here. Okay, cool. Well, we're just doing Grover Oracle, and we're doing 5-1. Let's see what happens. See what happens. And we are in with 30 minutes right now. What the hell is going on? London missing one card. N. What? Oh, yeah. Sorry. So it's basically NB qubits, right? NB qubits. Yeah. There should be NB qubits. Let's see. Oh, that's beautiful. That's beautiful. Okay, but I've missed something in here. So I'm missing one X, one layer X in here, right? Am I? Something is not right. Wait a second. Something is not right. So I'm calling 5 qubits and NB value is 1, right? So for the NB value is 1, so yeah, that's it. So NB value is 1. Okay, but we're getting the NB value of that -1. Okay, that's what we're getting because we're. If I say 1, I want to kind of have the control Z for the zeros, right? Run code. So that should auto generate us the. Yes, beautiful. Look at this. So 0, 1, but still, why 2 times? What are we doing here? It's what are we doing here? Oh yeah, well, we don't need that obviously anymore. We don't need that obviously anymore. Look at these. Look at these. So now it works. So now we're doing these, and it kind of generates an oracle that flags one element here. Bam. Now we're going to say, please flag 5 elements. Run code. Nice. So you see, so this is one element, right? So can I paint on this? I don't know. Yeah, so this is one element, second element. Something's off with the. So something's off here with the. No, I think it starts from. Wait a second. Is this working well? So something's not working well again. But we have like 1, 2, 3, 4, 5. Multi-control things. They are not being painted in a nice way. Or printed in a nice way. Because of the X gates in here. But maybe we should do this with the momentums, so it kind of maybe it's clearly organized. What was that with them with the not momentum not momentum but moments. Tutorial circuits gates. Moment. Okay, so that's a moment. It's just that. Okay. Circ moment. Okay, cool. So I can basically, what I can do is I can say, hopefully this is going to print it nicer. So I just can say that, so M1 is a circ moment, okay? Can I just append to the circ moment? Probably I can. So I'm appending this to this moment. Now this is one thing, right? So this is M2 equals circ moment. And now it just basically, instead of yielding it, we're going to say M2 append this operation. And the same is going to be for, M3 here in the last layer. So I'm going to do M3, and then we're going to say, so M3 append this. And hopefully this will work. And so at the end of the whole thing, what we do is, we kind of have to return a circuit or what? Circuit, and now we're saying, is this the way that we're supposed to, this is supposed to work? Circ moment. You're creating it like that. Okay, so you're kind of doing these like these, and you're just doing M1, M2, M3, or basically return. So you're returning a circuit with these 3 moments. Let's see what happens. Yeah, run code. Let's see that makes it be more clear. It's not sure to append. Okay. So how do we add stuff to a moment? So you can just create it like that. Constructing circuits, circuit append. The operations it can be, for example, is a moment with poly x is 3 qubits. This is the operations. Circuit append, moment. So what I just can't say moment. Can I just take a look at the API of this thing? Circ moment. On qubits with operation. With operation. But with a given operation added. Okay, so with operation. Okay, so I'll just go and say, so sorry, how is that written? With operation. Well, operation. Boom. What have we got in here now? No. It's actually missing. Cancel. Positional argument operation. No way. What have I missed in here? So where? Line 63. I know, but that's not 18. Okay. Here, with operation. Where? Where is the operation missing? The operation to append. It returns a new moment. Do I have to kind of initialize it like this? No, it shouldn't be a problem. This is basically, it returns a moment. So you're kind of have to do like these. Or, stupid, kind of like this, right? So M1. I don't care about stuff not working well, so this is just, so this is just, circ moment. Circ moment. What's the problem? Circ moment. Ah, so what's the problem? Create qubit object has no attribute qubits. What? I don't get it. I don't get it. Line 62, line 17, when you do these qubits. Fine, but it's like create qubit object has no attribute qubits. Effective qubits. Why is it? What the hell is this? This is an operation. So why isn't this working well? Why isn't this working? Returns. Methods. Qubits operations and qubits. Why isn't this working? Probably should open the light because it's getting dark in here. Approaching the hour. So why isn't this working? Moments, circ. What else can I do? So operate on. Determines that the moment has operations touching the given qubits. With operations, moment qubits. Is it that I need to give it the moment? Qubits here works. Come on. CZ and X. Qubits here. Qubits 2. So what is it? What is the problem here? So what is the problem here? It's telling me that Greek qubit object has no attribute qubits. Because I'm creating a moment with qubits X. And these X. Wait a second. This is actually okay for M1. So this is here. This qubits is defined in here. Okay, but moment. Why isn't this just working? Come on. This is an array. Okay, this is an array. It's an array of operations. Is an array of operations. Is an iterable. Is an iterable. So this should be a list. That's what this is telling me. It cannot just be an operation. Probably. No. It's fine. It's not fine. That's fine, right? Or maybe it's iterable. I have no idea. I gotta try something. So what the? So this is. I cannot just. Maybe it's because of it's got to be an iterable. So maybe maybe I just gotta do these sort of here aside and say OP equals these. Is this gonna pass or not? Maybe it's because of the reference. Yeah, maybe it's because it's passed as a reference, and so yeah, it passed because now it complains about M2. Okay, that's not bad. That's not bad. So it complains about M2, but why? This is gone. What does it say now? Circ, line 24. M2 equals circ. And so, I don't know. Maybe that was the error that I was getting before, to be honest. Okay, now M3 has not known. I'm so stupid. I'm just so dumb. Why am I that dumb? First, that works here as well. It's just gotta be an equal, right? So dumb. I'm so dumb. Yes! Now, finally, now it works. For once. Or not. So, what have I done? Well, I gotta yield that, baby. I gotta yield that because it's gonna yield multiple circuits. Yeah, and I'm gonna yield that in here, baby, inside the loop. Yeah, and now I should see 5. 5, 5, 5, 5, 5, 5, 5, 5, 5. Please. Okay, I like that. I like that more. I like that more. No, I don't like that at all. Where are these egg sandwiches, man? Where? Ah, come on. I think I'm just. I think with operation. You know what? I think it was correct in the very beginning. I fear M1 equals M1 with operations. With operations? With operation. And there's just a dem operation in here, okay? Just a dem operation with operation. Dem. This friend should be created in here. So what is the problem? What's the problem? Why doesn't these work? You create the moment and then you add the operations to the moment. Run the code. But it's there. But it's there. Line 18. It's there. Or do I just have to give it a stupid name? source with operation. Circ, moment with operation. With operation. How is it used? Where is it used? With operation like that. Okay. Okay, so first of all, let's kind of do this. I don't know how this works. In creating or create a new moment, and that's not what I want. This must work this way. Come on, you gotta be kidding me if not. You gotta be kidding me if not. So then you just going back to this thing with operation, just the operation Z, circ, not circ, but M2 with operation. This is M3 with operation, and just get rid of the brackets in here, get rid of this thing here. So now we've got M1 circ moment, and then M1 equals M1 dot with operation, just the operation, right? Why wouldn't this work? What am I doing wrong? Something really, oh, now it works. Okay, but it's still, this is not thrown in a nice way. I'm not like, how, maybe I'll just add a, I want to make sure that it's building the right circuit. That's my whole point in here. Because I've done the whole thing with the moments for nothing otherwise. So it yields the circuit with the moments. That's a moment. How can I paint the moments? Okay, so the moments are not painted, like, truth be told. Let's start small. Go in 2. So what does it do? What does it do with 2? Okay. Yeah, but that's not what we want. So we definitely don't want these around the place where there's a Z. Okay, so this is not correct. How are we doing with this? Okay, cool, got 10 minutes. So definitely, so with a layer of X gates, but not there where there is going to be. Oh, no, actually it is. It is fine. That's fine. That's correct. Because this is the 0 and this is the 0001. But I want this reversed, to be honest. To be honest, I want this reversed. But okay, let's say that's fine. I don't care whether it's reversed or not. So if I say 3, but that's fine. Then it means that it kind of works. So this kind of works, right? So now I got 3. Those things just get moved. These, and then it just moves in here. Okay. Yeah. Seems fair. Seems fair. So I think it's fair, yeah. That works. Okay, cool. Seems to work. So I can basically now create any combination of so any kind of oracle that flags a given amount of numbers. So what I'm trying to do here is basically I'm gonna call this basically, I think I'm gonna call this Grover diffusion. Grover diffusion. And so diffusion is always going to be the same, right? Put in here Grover diffusion. Always going to be the same. If I run the code now, it's always going to be these. Yeah. No matter what. That is actually, it does not depend on NB values. So we can get rid of these, right? And exactly. So what you have, or we should have in here is, so we got the qubits. And so we'll also have so we're going to have another function just as a helper function in here that's going to yield us just a bunch of just a layer of Hadamard's everywhere. Okay, so this is going to just yield us these, so we can get a bit more. Okay, so now we kind of have diffusion or an H layer. Okay, kind of now basically have something here where we can just say append, okay, append, and now we basically can say an H layer and the qubits, okay. So we got an H layer. Then we apply a Grover oracle that flags. So it's got NB qubits and it flags NB values. And then we've got basically Grover diffusion, okay. So, and this is NB qubits. So, and these should be, if I run this code, now we should have a fully functioning Grover iteration. So the first layer, then the oracle, and then the whole thing at the end. Good. So if we do 3 qubits and we are flagging 1 value, and that should work like Grover's algorithm. So if I'm going to test this now, I'll leave it here. So yeah, so this is these, then we flag 1 element, then we do Grover's, and then we can measure. And so this would basically flags the element 111, right? So if I now basically how does it work? So I can just use these, right? So I'm printing the circuit, so I can do also basically strange works print, right? That was supposed to print me stuff in there. Atom resolver, I think it's not needed. Simulator run. Is it gonna catch the results automatically if I just run this? Is it gonna do this for me? Is it gonna do this for me? Stranege works. Right in time, I think right below an hour, so it's perfect. Output. So something's broken in here. What is it broken? Circuit has no measurements. Yes, circuit has no measurements. That's true. That's true. So we're gonna add a so we're gonna apply a circ measure. I think that works like these, right? So measure. Where is measure? Circuit. Gates. Measure. circuits. What does the measurement look like? Circuit measure. Do I need to add target? Circuit measure. Just Google that. I cannot find an example of these or what? Qubit with a key. Okay, we don't care about the key, so we're just gonna measure these for everything, and now it should work. I get my latest result. I hope so. Okay, finished. Correct. Okay, cool. That works. That works. Perfect. So it seems to work. If I basically now say, please select me two values, right? Then it should kind of do the 000, right, and the other one. So yeah, perfect. You see? You see? Okay, so now I have a fully functioning Grover, something to generate Grover algorithms, sort of Grover circuits, right? So that's cool. My next step is now to kind of go and do these, right? So basically, we'll kind of, the H layer is not going to be like that. So the H layer, we're going to have like, so I'm going to have to change that a little bit, but we're going to go and implement these as a, okay, we can just do a Hadamard layer all over the place. That really doesn't matter because we want that in the Plastid anyway. And so what we're going to do is then we're going to try to control an entire iteration of Grover, and then we're gonna try to do this and measure that qubit. And so these should be, what I want to find is, I want to find correlations between, I want to kind of prove that there's a correlation between these 62.5% and the number of elements that this Grover iteration is fine. That's quantum counting, and I want to kind of see how much accurate this is as we increase the number of qubits and all this kind of stuff. Okay, which is kind of essentially a little bit, it's a bit of a different approach than the actual full-blown quantum counting, where you just do, you actually do quantum phase estimation for that. But we'll see. So now this is kind of fully functioning. So next time I'll just probably do a bit of documentation in there. Okay, but that's nice. So I like the concept of how you can generate things. I think the momentum stuff is not really needed in here, but it just helped me understand that. Can you have the layers and construct the whole thing? So, but I'm struggling, as you can see, I'm struggling with the Python part a little bit, but it's fine. But I guess it's kind of fine, because this you could do it probably in a bit of a different way, for sure, in a more compact way from a Python perspective. That's not a problem. Perfect. We'll leave it here.